So in chapter 2, we start talking about atoms in the periodic table, and we begin with an overview of different atomic theories. We start with the ancient atomic theory, the earliest atomic theories, and then we update that with the modern atomic theory, and then look a little bit at how that is applied to classifying pure substances. So, as we mentioned earlier, we take a atomistic view of matter in modern chemistry. And the atomistic view of matter was, as far as we know, first written down by a guy called Democritus about 2,500 years ago. And we follow the same general principle that he outlined, which is that we consider matter to be composed of particles that are called atoms, that are indivisible by either physical or chemical methods, and then these atoms are simply the building blocks that we piece together in different ways to create all of the different types of matter that we see in our universe. So it's kind of like, as I mentioned previously, the building block view of matter, and the atoms that we're talking about here are like the different sizes and shapes of the building blocks. Now, it wasn't until 1808 that an English schoolteacher by the name of John Dalton formulated the first modern atomic theory and set out its general postulates. And this is normally broken down into 5 big key ideas. Your book gives 4, but I think 5 is more common. Now, he wrote them down in sort of the language that was common in 1808, so I'm kind of paraphrasing here and I'm updating the language. Now, John Dalton was an interesting kind of guy. He had a whole bunch of different scientific interests, and he was interested in not only the atomic theory, but also things like the weather, and he had interest in medicine and stuff like that. And one of the things that's interesting about Dalton is that he suffered from color blindness, and he studied this on himself. And for that reason, color blindness is sometimes referred to as Daltonism. So that's kind of, cool that he was the first guy to systematically study color blindness. So I list out here Dalton's 5 postulates written in the modern language, as I mentioned, and I also kind of add a little bits of information where we know that he was a little bit off the mark with his theory. So his first postulate is pretty familiar. He says that all matter is composed of tiny indivisible particles called atoms. So he's just kind of like restating what Democritus has said. What we now know is that there are 118 different types of atoms. These correspond to what we call the elements. So these 118 different types of atoms are assembled in different types of connectivity and in different ratios to create all of the different varieties of matter that we see in our universe. The second of Dalton's postulates states that atoms of one type are the same as each other and different from other types of atoms. So what he's really saying is that every type of carbon atom is the same. Every type of oxygen atom is the same, but carbon atoms are different from oxygen atoms. In fact, carbon atoms are different from every other type of atom, is different from the 117 other types of atoms, right? Now, what we now know is that this is not quite correct, and that there can be like families of atoms of a different type, and we call these isotopes. So we're going to learn a little bit about that later on. So what I'm really getting at here is that we now know, for example, that there are 3 different types of hydrogen atoms. Dalton didn't know that. We'll explain how we get these 3 different types later on. Dalton's third postulate kind of explains why we see the more than 118 different types of pure substances, and why we see different types of pure substances. And what he's saying is that in postulate 3 is that the number and arrangement of atom types in a pure substance determines its identity. So try and give a little example of this on what little white space I've got here. If I have 2 compounds, one is familiar, H2O, that's water, and I have H2O2, I can see that these guys are different because one has an extra oxygen, right? H2O2 has an extra oxygen, so they don't have the same number of atoms of each type. And so that's going to make them different compounds, and that's a good example of that. Now, if I look at something like where the connectivity is an issue, let's say I have this compound and it has 4 carbon atoms, and then it also has 10 hydrogen atoms. Okay, there we go. Okay, so it has a total of 4 carbon atoms and 10 hydrogen atoms. Now, it turns out that there are other ways of connecting 4 carbon atoms and 10 hydrogen atoms. I'll try and show you now. We don't have a lot of space, but let's see how we go. What about if we do this? 1, 2, 3 carbon atoms, and then I put my 4th carbon atom there. And then now I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 hydrogen atoms. So what I've got now is I've got 2 different things that both have the same number of atoms, but how they're different is the way that they were connected. In the second one here, I've got the carbons kind of in a T shape, and then I'll just draw you what I had for the other one. And in the first one, I had the carbons connected in a line. And the difference is just in the connectivity, right? And it turns out that those are 2 different compounds that have different physical and chemical properties. They're 2 different pure substances. So the nature of a pure substance depends upon not only the number of each atom type that is present, but how those atoms are connected to one another. And you can think of that in terms of those Legos models that I was kind of referencing earlier when we were talking about the atomic theory. You can connect the same number of building blocks in a variety of different ways by having them in different arrangements, right? You get different things. Okay. So then postulate 4 of Dalton's atomic theory remains unchanged to this day, and it says that chemical change involves the combination, so that's sort of like, you know, multiple atoms coming together. Let's make it make some water. So 2 hydrogen atoms coming together to form with 1 oxygen to form water. The combination of atoms, the separation of atoms. So say we had, I'm trying to think here. Say we have carbon dioxide. Try and make some space there. And then that can come apart and it will make carbon monoxide and leave over an atom. Let's not put these dots on there. That's just going to confuse you, isn't it? You don't know what those mean yet. We'll have to work on that. But that's the idea. So that would be separation, and then rearrangement, where you can think about those 2 compounds before, where we had the linear and T-shaped arrangement of the carbon atoms. So that kind of makes sense. You're just reorganizing how the building blocks are connected, right? You're breaking some apart, you're making new connections, you're reorganizing the order of things. Okay, so postulate 5 of Dalton's atomic theory, pretty simple. It's exactly the same as what sort of Democritus was hinting at. We say that atoms cannot be created, destroyed, or transformed in a chemical reaction. So by simply just mixing together different types of matter, you can't create atoms out of nothingness. You can't have atoms be destroyed and get converted into nothing. And you can't transform one type of atom into another type of atom. So we now know that by the process of what we call nuclear reactions, where we put lots and lots of energy in, we can get some of these things to happen, but we certainly can't get these things to happen through a chemical reaction where we're just simply mixing multiple different types of matter together. So you're stuck with what you've got as far as the types of atoms that are present. You can't get extra atoms out of nothing, you can't make an atom disappear into nothing, and you can't convert one atom into another kind of atom. You can't turn a nitrogen atom into a sulfur atom. You can't turn a sulfur atom into a carbon atom. It's impossible. You're stuck with the collection of building blocks that you start with. So how big's an atom? An atom is about 10 to the minus 10 meters across. So I have to count here. 9 zeros and a 1 to the right of the decimal point there. So that's pretty darn small. We can use an instrument called a scanning tunneling microscope, STM. This was invented by some guys at IBM, and they actually won the Nobel Prize for this work. And they used it to image the surface of silicon, which is used obviously to make silicon chips in computers, which is IBM's business. Now, the original images that they got off the surface of silicon were a little fuzzy, but you could definitely make out individual atoms. This is a more modern image. And the guys that invented the scanning tunneling microscope, they realized that they could also move atoms around using it, and they were very wise. In their original publication, they demonstrated how they could spell out the letters IBM on a surface by moving the atoms around with this tool that they'd developed. And so they created the world's smallest billboard for IBM, and their bosses were very, very happy. So it's a pretty simple kind of idea. Is they have a really small tip, and on the perfect tip you just have one atom at the very tip. And then what you do is you bring this tip really close to the surface of your sample, and to your sample you hook that up to one terminal of a battery, and then you hook the tip up to another terminal of your battery. And what's going to happen is electricity will flow from your tip through your surface. It'll make a little circuit there. If you have just a tiny little gap between the tip and the surface, but as it goes over the bumps of the atoms, it'll get a little closer, right? And you'll get like more electrical current flowing, and you can monitor that and turn it into an image. So basically this is an image of the extent of current flow as the tip is moved across the surface. And when it's a little tiny bit closer, you get more current flowing in, so you can get the shape of whatever is on the surface. So that's kind of cool. And one of the things they found, as I mentioned, was if you lower the tip down and you then pull it away, you can get an atom to stick to the tip, and you can move those atoms around. So that's kind of cool. So atoms can bond to one another, form what we call a chemical bond, and create what we call a molecule. So a molecule is just two or more atoms chemically bound together. We have a little naming convention. If our molecule is composed of two atoms, we call it a diatomic molecule. And if our molecule is composed of three atoms, we call it a triatomic molecule. Now, if we're sort of like, greater than three atoms, we tend to kind of just call it a polyatomic, and poly, means several, like a polygon in geometry. So it's kind of a wishy-washy statement, meaning, more than a few, more than just sort of 1, 2, or 3 is generally what we mean by a polygon or a polyatomic molecule. Now, it's important to recognize that the atoms that are in molecules can't be separated by physical processes. We have to break the chemical bond between the atoms in order to separate them. And I also hope that what you realize in this example here, this is an O2 molecule, O2, is that the atoms can be of the same type or they can be different from one another. Sometimes you'll hear people describe a molecule as being the limit of physical subdivision. You can't get any smaller without beginning to, or you can't break a sample of matter down into smaller units without breaking chemical bonds. So in a kind of, hand-waving colloquial sense, molecules behave as a single discrete package of atoms, right? They're just a little bundle of atoms. So the reason for mentioning molecules is because 7 elements are found in nature as diatomic molecules. These are hydrogen, and then we go over to element number 7, which can help you remember that there are 7 of these guys, and we draw a 7 to get the rest of them. So we have H2, N2, O2, F2, Cl2, Br2, and I2. And you do need to know those 7. There is a little memory aid that you can use to help remember them. Other than the going over to number 7 and drawing the 7, there's the have no fear of ice cold beer, and that gives you the initials for each of these molecules. So have no fear of ice cold beer, and so that should I normally use both, so that's kind of handy. Now there are 2 other elements on the periodic table that in nature exist in molecules, and they're right next to one another, and they're also right near what we call the diatomic 7. And so phosphorus is found as P4 and sulfur as S8. And that's kind of, remembering those 9 can be or is important. Okay, so a homoatomic molecule, homo just means same, that contains atoms of the same type. And, any pure substance that contains homoatomic molecules also must be an element. So here is an O2 molecule. Some of these homoatomic molecules can get quite big. For example, there are C60 molecules comprised of 60 carbon atoms, and there are even C70 molecules composed of 70 carbon atoms. Now I should point out that these are manufactured in the lab. We don't find them in naturally occurring samples in any sensible amounts. Now, heteroatomic molecules are slightly different. Heteroatomic molecules are comprised of atoms of at least 2 different types. So these are going to be always compounds, right? Because you've got atoms of different types present. So in this case, it looks like we've got a water molecule here, and we've got 2 hydrogen atoms and 1 oxygen atom. So you can see that we've got 2 different types of atoms there. That makes it heteroatomic. It also makes it a compound. Now, it is important to recognize that not every compound is composed of molecules. Some compounds are composed of combinations of electrically charged particles that are called ions. We'll be learning a little bit more about this later. So in these compounds, what you have is like an extended, approximately infinite array of positive and negative ions that attract one another, and there is no discrete little bundle of atoms. There are no molecules present in ionic compounds. So it's a little bit weird, because how would you write the formula of these guys? We couldn't write Na infinity Cl infinity. That would be weird, even though we kind of know that we have this approximately infinite array. What we do is we write the ratio of ions that are present in the smallest repeating unit, right? The smallest unit where the charges add up to 0. So you can see that that's here. I've got +1 being added to -1. So those added together give me 0 electrical charge. And that's going to happen when I have 1 sodium and 1 chlorine. So I would write the formula of this guy as NaCl. We're going to talk about ionic compounds a lot more as we go through the class, but it's important to realize that for ionic compounds, you don't have molecules. Okay, so now we can break down our pure substances into multiple different types beyond element and compound. So previously we were saying that we had elements where we had only one kind of atom present, and we had compounds where we had multiple types of atoms present in our pure substance. Now we know that the majority of elements are made of individual atoms that are not chemically bound to one another. However, there are 9 elements that are in nature found as homoatomic molecules. And what these guys are the diatomic 7, the have no fear of ice cold beer elements, and then we've got S8 and P4. Now, when we look at the compounds, we know that there are 2 different types of compounds. There are those compounds which are comprised of heteroatomic molecules, where the compound is made of atoms that are chemically bound to one another and act as a discrete little bundle of atoms. You know, maybe you just have like 2, 3, 4 atoms in this bundle of atoms. There is another class of compounds which we didn't talk about in great depth, but they don't have discrete molecules as their building block. Rather, they are an extended array of positive and negatively charged particles that we call ions. Okay, so that gives us a brief overview of the modern atomic theory with a little bit of history thrown in there as well. We talked about 2 key characters there, Democritus and John Dalton. And yeah, I hope you found it helpful.